Hello, today we are going through complex numbers, which is week 27. We have almost hit the end of the year, and maybe by this point in time or this week, your kids will actually know what complex numbers are, since it's been our domain all year, but I feel like at least my class doesn't necessarily know what they are. So hopefully this week, you as a director and our kids will finally know what this is. So let's jump right to it. First thing that we do, of course, is quick flip arithmetic, and I don't have my little set of cards, but I'm going to do the distributive property again this week. So of course, A times the quantity of B plus C is the same as saying A times B plus A times C. Okay, so the distributive property, we've been doing this most of the weeks for these last 10 weeks of class. And so the kids are probably pretty familiar with it, but the one thing that I'm going to do is the first go round, or at least the first couple rounds, I'm going to make one of the numbers complex. So let's pretend that I've drawn a 2, a 3, and a 4. So this will be my A term, 3 will be my B term, and 4 will be my C term, but I'm going to turn one of these into an imaginary number, so I'm going to make it 3i. So it's 3i instead of just 3. Okay, so if I plug that in, I have 2 times the quantity of 3i plus 4. Multiply those together, you get 6i plus, that distributed is the 2 times the 4, so you get 8. 6i plus 8. I can't make that any more simplified. You can do a few more examples where you're just flipping some cards, you're getting 3 values, and you're plugging those in for the A, B, C, and just having one of those be a complex number, so or imaginary number. So add in that I to it so that you have an imaginary number in here. The next thing that I would do is I would practice this at least once with having 2 of the values be an imaginary number. So I'm going to make my 3i and I'm going to make it 2i instead of just 2. So now I have 2i times the quantity of 3i plus 4. Okay, so I'm just plugging that in for these values and then distributing. So the 2i times 3i, we're still getting 6 because of the 2 times 3, but now we have I times I. So I times I is I squared. And remind the kids that if you just see something like I, or you just see a value, it's kind of like it has a little exponent of 1. And so this is kind of like saying I to the first with the power of 1, or the first power of I. There we go, I'm saying it right now. The first power of I times the first power of I. We just intuitively know that the I is there, so we don't think about it. And when we have exponents and we're multiplying numbers with exponents, what do we do to the exponents? We have to add those together. That might be a new concept for a 7th grader. So that would be something to show them. So if I have I times I, that's the same as if those index values were 1 on each of those items. So it's 1 plus 1, so it's I squared. I squared. So we have 6I squared, okay? And then here we're multiplying the 2 and the 4, so we have 8I. And that time we only have a single I, so we don't have an I squared, we just have a single I. Now at this point, I squared, you can say, what is I squared? What does that equal to? And maybe you'll have a student in your class who knows that that's -1. And if you don't worry. I feel like a lot of kids would not have gotten that at this point in time. And let's talk about why maybe they won't know that this is -1. Or if you're watching this as a director and you said, I didn't know I squared was -1. I'll tell you why you don't know that. And then we'll go through how you're going to know what it is and why it is what it is. Okay, so heading back to week 2, number notation, you go through your number notation. This isn't in the eye charts, but on student page 1, about halfway down, it says study the pattern and memorize. And that is the only time, at least that I have found, where you see anything with the I values and what they translate to. And so I actually, at the point that we saw this, I made my student write this out, my daughter, write this out on a note card, and then she kept it at her desk. And every time we had calculation problems that included an imaginary number, a lot of times you're getting it to the point where you might get an I squared, or I with a exponent of 3, or I with an exponent of 4. And she would know what those values were just because she'd go back and look at her note card. She didn't really understand what it meant. And hopefully after today, she'll understand how she gets to that. But if your students were maybe not fully doing the pages, especially those first few weeks, this was on week 2, they might not have caught this, or they might have seen it the one time and then never used it again. So I can see that there's probably going to be a lot of kids who do not know that I squared is equal to -1. And so what I plan to do in my class on Monday is when I have community day, is I'm going to either bring them some note cards so that they can write this out on a note card, or what I might actually do is I gave them brain books at the start of the year, and so I'll just have them take a blank piece of paper and write out those 4 things on their piece of paper. So what I mean by that is they will write that I with an exponent of 1, or just general I, is equivalent to the square root of -1, and then I squared equals -1. I with an exponent of 3 equals -I, and I with an exponent of 4 equals +1. So that's just a regular 1. Just have them write this out. They don't have to know what it means yet. You're going over it in today's lesson, but just have them write this out because they need to have this handy as they're going through calculations. They're going to be using this, and it'll just make it quick and easy for them to figure out an answer, or figure out when I can substitute -1 in where I had an I squared. And now all of a sudden, maybe I can keep doing a calculation that I couldn't do before because I couldn't simplify anymore having that imaginary number. Okay, so that is my little intro on the quick flip arithmetic, using an imaginary number so that they can see how to work that, and then making sure that they have this little thing either on a note card or in their brain books, because they will use this, and they'll use it again next year. So when they go up to monomials, they're going to see this again. The only time you're not going to see this is if you're still in one of the lower domains, so lower than complex numbers. So the reals and fractions and integers and numbers and all that stuff, I think they briefly might see this, but they're never calculating with it. They don't do that until complex numbers in Challenge A. Okay, so that was our little intro. The next thing we do is go over the exordium, which is looking at the cover page for complex numbers. And I always say, okay, so today we have artwork from Ralph Kunze, and I have some notes about this. So I would start with, what do you see? So I always ask the kids, what do you see? And I let them talk for a while. Oh, I forgot. We also open up before we get to the cover page, we open up the math map, we look at the compass page, and we say, where are we? So we're still in complex numbers, and as they scroll down to week 27, complex numbers, it is in ND, which they label as imagination. And then, so this is a good time to say, anybody know what ND means? What do you think they're talking about there? And maybe one of the students will say, well, it's the other dimensions that you keep going up to, because we did first, second, third, fourth, and now it's just going to continue, and that is the case. You can have a 5th dimension. You can have a 6th dimension. You could have maybe a 127th dimension. We don't really know. We don't know how far it goes. We can't really see or do anything with those other dimensions other than to kind of theoretically work them with mathematics, because we don't really exist in that dimension, or at least we don't understand how those dimensions all work. But yes, other dimensions, so other numbered dimensions. And it's not like summing them all together, it's just saying individual, like the 5th dimension, the 6th dimension. We're thinking of them all as their own individual dimension. So that is what N space is about. And imagination, It's not the same as make-believe. So we are calling these imaginary numbers, but it's not the same as make-believe numbers. They're not fake numbers. They're not fake numbers any more than negative numbers are kind of imagination numbers. We can't see a -3. I can't ask you to give me -5 of something, but we know conceptually that they exist, and imaginary numbers are the same way. It's a bad name, but that's another story for another day. Okay, so back to the cover. So on the cover, the artwork this week is a digital image from a German artist, and they made it with an app. And so the application that they use to make this makes fractals, which are kind of like these geometric shapes to explain things mathematically. We see fractals in seashells and a bunch of other things in our real life. And so these apps are helping kind of like show that. So this is pretty much a fractal image. And if you look at it, you can see this swirly guy kind of matches the swirly guy that they use for the image for ND, for the dimensional space that we're talking about. Then I would read through the C.S. Lewis quote and ask if they have any thoughts, and then the reflection, read through the reflection and see if there's any thoughts. And there's not a ton with my 7th graders, but I think that's one of those things that as you get into the upper level challenge years, they're going to have a lot of thoughts on those quotes and reflection because they've been reading stuff from those artists, writers and stuff over time. So that should be fun as the kids get older to see all the new things that they find in all the, during the math map, because they'll see the same page, but they'll have a different perspective. They'll be a different kid at the point that they're looking at it. So that's going to be fun as we go along with our kids. Okay, next thing we move on to is looking at the invention page. Okay, so it's the I2 frame page, the invention page, and we are looking here. We can have them kind of define end space. We kind of did that a little bit already. I would say, tell me what you know about dimensions. And they'll probably start telling you about stuff that we've learned throughout the year and how they understand dimensions, and that's great. Then they're showing a lot with vectors on here, and I love that they're doing the comparison of rectangular coordinates and then the polar coordinates. And so I just want to point that out to the kids. They can see it on here, but sometimes I redraw it on the board in a more simplified fashion so that I can make sure that they just understand it. So here we have rectangular, and then we have polar over here. And so in one dimension, we have a line, and they're showing us with vectors. Polar, we actually still have that too. In 2D, we have our x-axis going in our one direction, and we have our y. And for polar, we have our circle that is on that flat plane. That's supposed to look like a circle. And then in 3D, we still have our x and y, but now we have another side, kind of like this marker coming out of the board, and that is our z, right? So we have 3, and then for our polar setup, that's the same as we no longer have just a circle. Now we're kind of looking at a sphere, and that's my way of kind of drawing that 3D shape, what the sphere would look like. And so we still have a radius, and then we have our angles, our theta, but you're looking at that with that sphere. The next thing is to talk about, let's go back to kind of this first dimension, back to the first few weeks that you were in Math Map. And do you remember when you were in Math Map how we would label something on a number line? So I might have -1, 0, 1, 2, 3. So this number line is this the real number line or the imaginary number line? It's the real number line. So we would label this as the real number line. And then there would be problems where we would see it looks kind of like a number line, but it was going up and down on the page. And we'd still have values. This is all probably week 2, 3, somewhere around there. And we would label this because maybe they'd have this with I's. And we would know this is the imaginary number line. And so we would label it with an I. And we would constantly in 1D, if it was in this direction, it was the real number line. And the ones going up in this direction were indicating the imaginary number line. Now, as we get to 2D, and they had to separately exist. But as we get to 2 dimension, these lines can overlap at the origin, at the point of 0. Okay, so this is still my imaginary number line. All right, this is my number line for reals. This is my imaginary number line. This is not the same as a y-axis. That's why I'm drawing it in a different color, because it is not the same as saying this is my x-axis, this is my y-axis. It's not a y-axis. It's the imaginary axis, the imaginary plane. Okay, so try to just help them see my real number line is here. They intersect at 0, they can cross over, and then the imaginary number line is its own number line, its own plane. It is not the y-axis. Okay, 5 common topics. So for common topics, we have compare the expression of vectors. And so the thing I just wanted to highlight to my kids is to say, what was a vector again? Do you guys remember? And maybe they'll remember, especially if they're Despicable Me fans, they'll remember that vector has magnitude and direction. And we indicate it, we have the notation where it looks like this. So unlike just a normal line that could be indicated like that, our vectors have that little like half triangle on there. So that's our vector notation. And then define ND. We kind of did that a little bit when we were on our compass page, talking about how those are the additional dimensions. How is the circumstance of dimension expressed by R to an exponent power? And so pretty much still knowing that the real number line, that X, Y, and Z, that's still all just using real numbers. The imaginary number line is its own deal, its own plane. And then discuss the relationship between multiplying I and rotation. This, I think, is so important. It's so important I actually made a video of just this back in September, because I feel like if people watched that, maybe they would have a better understanding of I at this point. Okay, so here we go. But I have not shared this with my kids yet necessarily. So here's my number line. Okay, so I'm going to have 0 right here, and I'm going to have my -1. This is my real number line. Okay, but I just showed you how the imaginary number line intersects at 0. So down here, or up here, we have I, and down here we have -I. So if I'm in my real plane and I'm going to rotate rotate 1 time. Actually, I'm going to make this, my little rotation, a little smaller. So throw some math out there. Okay. I'm going to rotate by I 1 time. So I with an index of 1, or we always just assume the index of 1 is in there. So just I, we get to I. As I do another rotation is the same as saying I times I. And remember, this was like I with a 1 exponent. So when I multiply those together, I get I, and I have to add my exponent, so I get squared. I squared. So this is I squared, was at this point. So I squared equals -1, because I have come back to the real number line at this point in time. So I squared equals -1. If I do another rotation by I have now gone from I squared times another rotation of I. So I squared times I is I with an exponent of 3. So I cubed equals, where am I at? I'm at -I. If I go by another rotation of I, that's my I cubed times an additional I, which is I with an exponent of 4. So I with an index of 4 is, I'm back to the real number line, I'm back to 1. So as I'm doing these rotations, I'm going from the real numbers up into the imaginary, back to the real, down to the imaginary negative, back to the real. And as I keep moving along, that pattern still continues. So up here, if I do another I, that would be I with a 5th index is equal to I. I with a 6th index, our exponent, is equal to -1. I with a 7 exponent is equal to -I. And I with an 8 exponent is equal to +1. And that pattern will keep continuing. So if I see something that is a multiple of 4, I know that that's equivalent to 1. So if I had an imaginary number in a big equation that I'm working and I have, I with the power of 16, I know immediately that's going to simplify down to just +1 on the real number line, just a normal +1. And I can further go into my calculations. So simplifying, the reason you want to learn these patterns is so you can simplify with those complex numbers. So as they get into the higher level math, these complex numbers these imaginary numbers let us start simplifying down and figure out when do we actually hit back onto the real number line and we can swap in the real number values. Okay, there's a lot of other videos. I watched hours of videos to try to understand this. So there's a lot of stuff, and I have a whole length of MathMap videos on that other people have put together if you want to delve deeper. But I think the biggest thing for the kids to know is just when they get to I squared gets you to -1, I cubed gets you to -I, and then I with a 4th exponent gets you back to +1. If they know that, I think for the complex work that they're doing this year, that'll probably be sufficient. I don't think they work with any exponents that are higher than that. Okay. And then the last thing on my 5 common topics, authority. So discuss how a scale factor is an authority. So the scale value is how much to multiply by. That was like when we had the 2 times the 3i. So the scale value is that 2 times 3. But it's only showing you the magnitude. It's not showing you the change in direction when we're talking about vectors. All right. The next thing is to go through Memoria and arrangement. So if you're looking at the Memoria and arrangement page, which is this I3 page, the kids might realize, okay, yeah, I've seen some of these operations. And actually, if you look at the pattern, you have notation. Well, that was our number notation of week 2 of MathMap. Addition and subtraction, I think those might have been like weeks 3 and 4. Multiplication, division, I think those were weeks 5 and 6. Exponents, so powers as exponents, which is the exponentiation, which might have been week 7. So it's kind of following along what we've talked about in MathMap. So they might notice that pattern. If there's anything that they wanted to memorize from here, these 3 equations are kind of useful to memorize. So if you wanted to put together like flashcards for your student at home, those might be 3 useful ones to do. So you have Euler's identity for radians, and then Euler's formula, and then, okay, let me make sure I pronounce his name right. Dumouvra's formula is the last one. And so if you wanted to memorize something from this page, that might be what's worth memorizing. Okay. Those are kind of the main things I'm going to pull from there on that. Then on the charts, as they're looking for through the charts, there's kind of 2 main things that they want to make sure the kids are getting out of this week. out of those charts. Let me erase this real quickly. Okay, the first is, what is a complex number? So, complex number, I actually asked this on my blue book. I said, what would you say to an Uprising Challenge A student for next year about complex numbers in the math map? And a lot of them just said, it's not as scary as you think, you'll get by, you'll get through, which were great answers, and I'm glad that they were positive about it. But I only had one student who was able to say it was real and imaginary number combination. So I feel like this is something maybe my kids have not been picking up. And so hopefully this week we're going through it enough where they'll understand it. So complex numbers, and we're showing that with our Z equals A plus BI. And the A is just representing a normal real number. Okay, so this is a real number. And the BI is representing an imaginary number. And we know that because we see that little I right there. So imaginary number. So when you combine a real number and an imaginary number, you get a complex number. That's it. That's all they are. And we've been talking about stuff with imaginary numbers all year. So they really don't need to be scared of them. Now let's look at what this actually looks like on a graph. And I'm going to throw the graph back up here that I did earlier. So here's my real number line. And let's go all the way down like to -2. Oh, +1. Here's my 2, 3. Okay, that's my really sloppy one. So this is my real number line. Here's my imaginary number line. I'm going to put it in a different color because I do not want them to confuse it with the y-axis. 1i, 2i, 3i. And then I'll go down into negatives. Okay, so if I were to take a point on here, let's say over here and right here. Okay, that is a complex number. That's the coordinate for a complex number. What is my complex number right here? Well, on my real number line, well, here, let me write out the equation again. To remind everyone, my complex number is my real number plus my imaginary number. So my real number at this point is +3. And my imaginary number at this point is +2i plus 2i. Okay, if I wanted to go down here and grab that coordinate, I would say, what's my real number on here? -2. And what's my imaginary number? -2i. So I could either say plus -2i, or I could have just said -2i. That means the same thing, right? So that's my coordinate here. This is my coordinate here. So because we're talking about complex numbers, we have a real part, we have an imaginary part, and so our coordinate is always going to have both of those components to it in order to know where we are throughout our quadrants, because I need to know my real part and I need to know my imaginary part. So when we're plotting those, we have to use that. And they do some of these in their student problems, so it's probably good to do this one example for them so they know how to find that. All right. Okay, so that's all I have on there. If you go to the actual student pages, we're back to mostly focusing on the tops of the student pages as being kind of like the highlight or the most important part. And so this first one, they're showing you on the polar, so they have that circular or spherical look to it, and they're showing you calculations, and then they're showing them on the rectangular coordinate, and they're showing calculations, but they don't actually solve anything on this first page, so I won't be assigning that to anybody because that's boring. Nobody wants one where it's already done for them. you could probably just look through it with the students and say, take a look at that one if you need help working through yours. And so then I'll divide them in groups of 2 to do the tops of the next 3 pages so they get through all 4. And so on here, oh, they're showing, that's exactly what we just saw with the I, the -1, the negative I, and then the positive 1. So they're going through and seeing that same thing. Or actually they're showing the degrees, how many degrees you're at for all of that. Okay, so that's not quite the same one I just showed you, but this, they're showing the degrees at these different parts. And they're showing the complex number that you would have at those degrees. So what's your real value and what's your imaginary value? And then they do the same thing around here, rotating. So they get to do that on page 2, and then I think 3 and 4 are the same way. Yes, so 3 and 4 are kind of including something with complex numbers and looking at it on those planes. So kind of like how that coordinate lays out. So I think they're going to get it a lot better this week than maybe they've understood it any of the weeks so far. And hopefully you as a director feel like, okay, I'm finally starting to get how this whole complex number stuff works out. I did calculus in high school. I did math in undergrad and graduate school, but I, not like upper level calc or anything, but I don't remember ever learning about complex numbers. So if you feel like, I don't remember ever learning this, I didn't learn it either. So we're all in the same boat. And they were still around when we were younger. It's not, they've been around for like hundreds of years. So even we are not old enough to be born so long ago that they didn't have complex numbers. They did. I just apparently didn't learn about them. Okay, so I hope this was helpful to you and it gives you something to talk about with your 7th graders this week. Thanks so much for watching.